When we last looked at solving exponential equations, we were able to find a common base and then ignore the base. In this lecture, we want to solve exponential equations again, where logs are going to be required. Logs are required when a common base cannot be found. And again, there are generally two types, those with x in one exponent and those with x in two exponents. It makes it so much easier for you if you learn the difference between these two types of equations. Because when we have x in one exponent, all we have to do is change it to log form. Just make sure you isolate your power. Remember at the beginning when we were changing back and forth between logs and exponential form, we always had to isolate our power first. Here, our power is already isolated. So to change it to log form, log base 2, the base is always the same. The answer to a log is always the exponent. So our argument goes here. That's it. This is our exact answer. I am not looking for decimal answers here. Never. We are not using calculators. And then we have those equations where x is in two exponents. So notice we have a power equal to a power, but x is in both of them. What we want to do first of all is apply a log of any base to each side. So we're starting with that property backwards, m equals n, and we're saying we can apply a log of any base to both sides. But of course, our base has to be greater than 0, not equal to 1. I usually use the common log or the natural log because they're easier to write. So here, let's apply the common log to both sides. That means I don't have to write my base 10. So we're being a little bit lazy, but that's okay. Next step, we're going to write the powers as factors. Remember that property? It said we can write these powers as factors. Now, you should be noticing that these powers are binomials. That means we need brackets here because all of this is multiplying, not just the 2. So be careful, make sure you're using brackets there. And in fact, to remind you, step 3 says you need to open the brackets. So if you didn't have brackets, put them in. We're using the distributive property. So now we have x times the common log of 5 minus 2 times the common log of 5 equals 3x times the common log of 3 plus 2 times the common log of 3. It gets a little bit confusing, so you have to remember what you're trying to do. We're trying to solve the equation. That means we want x equal to something. So we want all of our terms with x on one side of the equal sign, all of our terms without x on the other side. Why don't you do that writing and I'll do it as well. A little bit of color might help here. These were the terms with x. We wanted them both on the same side, so I subtracted the one on the right. These are the terms without x. I want them both. Oops, did I say right before? I mean right this time, the other right. So make sure your terms with x are on one side, your terms without x are on the other side. Now we see that x is common. So we can factor out that x. And just divide both sides by that factor. X equals everything on the right divided by our factor on the left. Now this answer is absolutely fine. You don't need to simplify it any further. Sometimes you might see in a textbook that they took those powers and wrote them as, wrote those factors as powers. So we would have log base 10 of 3 squared plus log base 10 of 5 squared all over log base 10 of 5 minus log base 10 of 3 cubed. Of course, you could evaluate those powers. But it's not necessary. Pearson is perfectly fine with you leaving it the way we had it in the first place here. Now, why are we not checking domain restrictions? I'm just saying this is your answer. It doesn't look very nice, but it is our exact answer. We don't need anything else. And we don't need to check our domain because this was an exponential equation. Think about the graph of our domain. Think about the domain of our exponential function graph. It's the set of all real numbers. That means there won't be any restrictions that we need to check.